Hello, and welcome to lesson 36 of this introduction to calculus with Wolfram U. The topic for this lesson is slope fields and Euler's method. So let's begin with a brief overview of the lesson. So the fact is that some differential equations are very difficult to solve by hand. So for example, here's a differential equation that looks quite simple. So y prime x equal to y of x the whole square minus x, and you want to solve it with the condition that when x is 1, then y is 0. Now, the function tsolve can certainly solve this equation, but the solution is huge and involves these so-called Bessel functions which occur in the oscillations of membranes and elsewhere. Now, in such cases, it is much easier to just visualize what the solution curve looks like for any initial value. So in this lesson, we learn how to use slope fields to see the behavior of such differential equations. So as an introduction to slope fields, let's consider the differential equation y prime x equal to f of x comma y. So if you want to find a slope field for this equation, what you do is you plug in the values for x and y in the function f and then plot the slope at that point. What does that mean? It means that you draw a small line segment with slope close to the value you get from the expression f of x comma y. And then you get a slope field which gives you a very general picture of the solutions to differential equation. It's not very precise, but it's good enough. Now luckily, we have two functions in the Wolfram language. There's stream plot and vector plot, which can be used for this purpose. So for example, let's go back to the earlier differential equation, and you can use vector plot by saying 1 comma f of x comma y over here, or stream plot with the same kind of specification, and you get back the vector field, the slope field over here, and the stream field over there. The stream field has the solution curves instead of just the arrows like over here. Now, in some cases, what we really want are the particular solutions to the differential equation. So for example, in the first case for our introduction, we had the differential equation with the initial value y of 1 equal to 0. And to find it out, you can use the stream points option, like over here, and get the particular solution curve on the vector plot or on the stream plot. So a couple more examples. Here's the vector field for x minus y, the stream plot. And you see over that when x is very large, then you have a positive slope from the expression over here. When y is very large, you have a negative slope. And the same thing can be worked out with vector plot over here with the initial value y of 0 equal to 0. Okay. Another example, let's take f to be x times y. Now what happens over here is the stream plot depends upon where you are. So if you're in the first or the third quadrant, then both x and y are the same sign, so you have positive slopes, and just the opposite happens in the other two quadrants. And if you want the particular solution, y of 1 equal to -1, you plug that over here in stream points and you get back the plot for that particular curve. Okay, so now in practice, you might just want to estimate the solution for a differential equation, and that can be done with Euler's method. The idea is this. Here's the same example from the introduction, and you want to find the value at 2, starting with the value at 1 equal to 0. So what you do is you start with 1 comma 0 and plug it in the slope over here. So slope is -1. And then write down the linear approximation, which is y equal to negative x minus 1. And if you plug in 2, then the approximate value is -1. But of course, what you could do is you could go off a little bit on the tangent line, then change direction, and then that will give you a better approximation. So for example, you could go halfway from 1 to 2 up to 1.5, and then you could change your direction with the new slope, and you get a better approximation from the linear approximation over here, and you get back solution at 2 to be negative 0.125. So here's the idea behind Euler's method. The idea is that when you take very short steps along tangent lines, you get much better estimates. And basically what you do is you use an equation of this type over here where every value of y depends upon the previous value. So here's a visual for the case where y prime equal to y and y of 0 equal to 1. Now of course in this case the exact solution is just e raised to x because its derivative is itself. So if you have only one point, then you get back just the tangent line, the red line over here. If you take 2 points, you go halfway down, then you change direction and you get a better approximation. And then of course you could take 3 points, 4 points, etc. By the time you get to 10 points like the green line over here, then you get a really nice approximation. And of course the topmost graph is the actual solution. So with Euler's method, the approximation improves as you take more and more points. So you have 1 point, then 2 points, then 10 points, and then you get closer and closer to the solution. Now, Euler's method relies on so-called recurrence relations. So what's that? Well, here's a relation for Euler's method. And what happens is, let's say you want to find the value of y2. So n is 2, then that depends upon y1 and x1. You need x1 and y1 to work out the value of y2. But then you say, oh, I don't know the value of y1, so to find the value of y1, you need the value of x0 and y0. But of course, those are just the initial conditions. So in practice, if you want to find, let's say, y100, you will need to go down all the way to 0, and that's of course a very tiresome thing to do by hand. On the other hand, it's a perfect thing to do by computer, so it's very easy to program on a computer. So after a couple of lessons, we'll talk about how to make a program that calculates the points from Euler's method. So that's the end of this lesson, and the main point is you can use slope fields to visualize the behavior of differential equations. We have two nice functions. We have vector plot and we have stream plot to plot these slope fields. You can use Euler's method to estimate a solution at various points. And because that's rather tedious to do, we can actually program it with a computer, but that you'll learn very soon. So the next lesson is about separate differential equations. Before you do that, do review today's lesson. It's an important lesson for differential equations. So I'll stop over here. Thank you very much.